In this lecture video, we'll introduce the idea of the traveling salesman problem. We'll also talk about Hamilton circuits and paths. Take a look at this graph. It has 4 vertices, and each vertex is connected to every other vertex with an edge. We're going to start at A and travel to each vertex exactly once and then return to A. The first question is, how many different ways can this be done? Let's list them out. Starting at A, we could first go to B, then C, D, and back to A. So there's our first route. Starting at A, we could instead go to C, then D, B, and back to A. There's our second route. A third option might be to start at A and first go to D, from D to B, B to C, and then return to A. That's our third route. There are actually 3 more routes. Notice that the routes in the second column are different from the routes in the first column, but they are related. Each route in the second column is the reverse of the route in the first column, meaning that it traverses the exact same edges, just in the opposite order. Now, let's meet Chantal. She's a businesswoman, and she needs to fly from point A to B, C, and D in any order, and then return home to point A. How many different ways can this be done? Notice on this graph that each edge represents a flight, and the cost of each flight is labeled. Also notice that this new graph is really the same as the graph we were just working with. The only difference is we have curved lines instead of straight lines, but that doesn't change the number of vertices and it doesn't change the number of possible routes. In other words, we already know all possible routes that Chantal could take. Let's list them out again. If Chantal takes this first route, she'll first travel from A to B, which costs $420. Then from B to C, she'll have the cost of $310. Flying from C to D will cost $115, and finally returning home will be $335. This brings the total cost of this route to $1,180. Notice that that's the same exact cost as if she took the same route but in reverse. That's the reverse route listed in the second column. Now let's look at the second route. She'll first fly from A to C for $425. From C to D will cost $115. From D to B is $500, and returning home, $420. This brings the total cost of this route to $1,460. Again, that's the same as if she first went from A to B, D, C, and back to A. The same route in reverse. Finally, she could first travel from A to D for $335. From D to B is $500, B to C, $310, and finally back to A for $425. So the total cost of this route is $1,570. Now Chantal knows all of her options, and we know the cheapest. There are 2 cheapest routes, A, B, C, D, A, or the reverse, A, D, C, B, A. So for 4 vertices, with each vertex connected to every other vertex, there are 6 possible routes, and 3 of those routes are the reverse of the other 3 routes. How do we know that this is the cheapest route to take? Well, we looked at all of the options. We calculated the cost of every possible route, which enables us to guarantee that we found the cheapest. This situation is what we call the classic traveling salesman problem, where we need a trip that starts and ends at one site and visits all other sites once, but only once. And when you find the route that is the cheapest, you have found the optimal solution. A traveling salesman problem has 3 main components. First, we must have some sort of traveler. This can be a person, a vehicle, or even a bug. Second, we need to have a set of sites. These are the places or locations the traveler must visit. We notate the number of sites that need to be visited with a capital N. Third, we must have a set of costs. These are the positive numbers associated with the expense of traveling from one site to another site. A solution to any traveling salesman problem is a trip that starts and ends at one site and visits all the other sites exactly once. And the best option is called the optimal tour, and this is a tour with minimal cost. Traveling through our graphs and visiting each vertex exactly one time brings us to 2 options. We can have a Hamilton path or a Hamilton circuit. A Hamilton path in a connected graph is a path that visits each of the vertices in the graph once and only once. That could look something like this. Starting with A, we could go to C, B, and finally to D. This is a path that starts at A, ends at D, and visits every vertex exactly one time. A Hamilton circuit has the added condition that we need to start and end at the same location. That is, we want a circuit instead of simply a path. For example, we could still start at A and first go to C, then B and D, but to make this a circuit, we must then return to A. That's the difference between a Hamilton path and a Hamilton circuit. And that will conclude this lecture video where we introduce the idea of the traveling salesman problem and Hamilton paths and circuits.